Okay, so let's take a look at example 1 of Stokes' theorem. So in this situation, we're given a line integral to compute, except the line integral itself is fairly complicated to calculate. First of all, because the vector field is pretty complicated, and also because the curve C consists of 4 line segments. So to calculate the line integral, you would have to separate the line integral into the 4 pieces here. So what we're going to do instead is to set up Stokes' theorem, where instead of calculating this line integral, we calculate this surface integral instead. Okay, so the first thing to set up the surface integral is to describe the surface S. So in this example here, because the curve C is sort of this slanted rectangular region that connects these 4 points, we can take the surface S to be the rectangular region that's inside C. And in this problem, it's already described that the rectangle is part of the plane given by the equation z equals y. But in any case, what I'm going to do is to determine S just from the 4 coordinates so that you can see where this equation actually comes from. Okay, so S lies on a plane. Right, so we need to determine this plane. So we need a normal vector. Right, so I can take 2 vectors in the plane, and their cross product will give me the normal vector. So let's say I take vector AB. So the vector AB would have, so it'll be B minus A to calculate, right? So that'll be 1, 0, 0. And then the vector AE, right? So if you remember back when we studied planes, you want the 2 vectors to have a common endpoint. So we start from A for the 2 vectors. So the other vector would be AE. So take E, subtract A, and you get the vector 0, 1, 1. Okay, so now we calculate the cross product. To get the normal vector for the plane. So let me just set up the determinant right above here. Right, so I need to calculate this cross product. So this times this is 0, and this times this is 0. So this is just 0 minus 0. Then for the j component, I have the extra minus sign. Right, so this times this is 1, this times this is 0. So you get 1 minus 0. And then finally the k component, this times this is 1, this times this is 0. So you get 1 minus 0. Okay, so I get that the normal vector is the vector 0, negative 1, 1. Okay, so now the equation of the plane. So the coefficients is the normal vectors, and then I can take the point on the plane to be 0, 0, 0 to keep things simple. Right, so it'll be 0 times x minus 0, and then minus 1 times y minus 0, and then plus 1 times z minus 0. And so this you get minus y plus z. And so z is equal to y. Okay, so so I get this equation for the plane, right? So again, the equation is already given to us as part of the problem. But I just wanted to do this calculation here to give you an idea of where this equation is coming from. Okay, so so now we need to parameterize S to be able to calculate the surface integral. So so I'm just going to use x and y directly as the parameters. Right, so in this because this instance x will be just x, y will be y, and then the z coordinate should be given by the the function for the plane, which is z equals y. Right, so this goes here. Okay, so so this is how we parameterize S. And what are the range of values for the parameters x and y? Well, you can see here that x goes between 0 and 1, and then y also goes between 0 and 1. So x goes between 0 and 1, y goes between 0 and 1. And the nice thing here is we've already calculated the normal vector. So the normal vector, we don't have to repeat this cross product, right? So this is already calculated previously as this vector here. Okay, so so that's the parameterization for S. And then finally, again, to set up Stokes' theorem, I need also the curl of the vector field. Right, so this is P, this is Q, this is R. Right, so I need to calculate the curl of F. So what are P, Q, and R again? So P is this e to the x cubed minus x. And then Q was e to the y cubed. Oops, this was a minus y. And this is a plus x. And then finally Q is the natural log of 2 plus sine cubed z. Okay, so so here we set up the calculation for the curl. Right, so it's this 3 by 3 determinant. Okay. So so what do I get? So the partial of y here is 0, right? Because this doesn't depend on y at all. The partial of z of this thing is also 0 because this doesn't depend on z. So this is just 0 minus 0. Then the middle component has an extra minus sign. The partial of x of this thing is 0. The partial of z is this thing is 0, right? Because this doesn't depend on x, this doesn't depend on z. So again, I have 0 minus 0. And you see in this calculation here, the curl is much simpler than the original vector field. Okay, so now the partial of x here is just 1, right? Because this term goes away. And then the partial of y of this thing is negative 1 because this term goes away. Okay, so I get that the curl of f is equal to the vector 0, 0, 2. Okay, so now finally we have everything to apply Stokes' theorem. So again, the original problem was to calculate this line integral, but Stokes' theorem allows us to replace it with a surface integral of the curl of f, and so to calculate the surface integral, we need to project it down onto the xy plane. Take the dot product with the normal vector and calculate this as a double integral. Okay, so this is how we calculate this surface integral. So now let's write it down. Right, so from before, we had the range of values for x and y to go between 0 and 1. Right, so the curl of f was this vector here, so 0, 0, 2. The normal vector was calculated here, so 0, negative 1, 1. And here it doesn't matter the order of the variables x and y, so let's just write dx dy, because in this instance where the lower limit and the upper limit are all constants, you can switch the order however you want. Okay, so here let's just calculate the dot product real quick, right? So this is just 2 times 1. I mean, this is 0, and this is 0, and then 2 times 1 is 2. And so this is just a constant, so you can pull it out. And here, since the function is 1, this is just the area of the rectangle for this region, right? So this is just a 1 by 1 rectangle. So I can just calculate it like this. And so the calculation is equal to 2. Okay, so again, basically the idea in this problem was to replace this closed line integral with this surface integral instead using Stokes' theorem. So this calculation was fairly easy. The only difficulty is to set up the surface integral, right? So you have to figure out how to set up the surface S. Here we had to, I mean, again, the equation for the plane is given to us, but if it's not, you might have to calculate it like this, then parameterize S to write it in parametric form, and then also calculate the curl of the vector field. Okay, so that's this example of Stokes' theorem.